Okay, folks. Okay, so welcome back. So today we'll be talking about large multimodal models. And first, for assignments, yes, please. Today from 2 to 3 and Thursday from 2 to 3, try to make time to meet with myself and some of the TAs to cover the progress on the projects. Hopefully by now you have medium progress towards implementing your ideas. That means either promising results and there's a clear path towards running more experiments and scaling things up, or the results aren't good, but you should have kind of done some error analysis and figured out where things are going wrong and have a good idea of how to fix it. So if you don't have those two yet, then please meet with us and we'll try to give both, ways of thinking about things that could work or ways of figuring out what might be going wrong. Reading assignment due tomorrow. In preparation for this Thursday's 5th reading assignment, it will be our large language models. There's 2 very nice papers. One is along alignment faking LLMs, where LLMs actually seem to be aligned, but you tease it apart and see its internals, there might be actually evidence of misalignment. And also one of the early works that really pioneered this modern space of LLM reasoning, done by DeepSeek in the mathematical domain. So ways of doing this third kind of post-training, reasoning, test time scaling dimension of LLMs. Great. So in today's lecture, we'll go from LLMs into multimodal LLMs. First part, we'll talk about just basics of multimodal foundation models, their architectures, their pre-training. Then we'll talk about adapting LLMs into multimodal LLMs. So whereas the first part is more about just training and looking at these architectures from its base, it's also a very popular set of approaches that take frozen LLMs and try to adapt it very quickly to get multimodal capabilities. And whereas the first two are still stuck within this space of generating text, condition on multimodal data, how do we condition on multimodal data and now generate also multimodal data? So that's going from text to multimodal generation and some latest directions. So recap, LLMs, we've all at least experienced, used some of these models before. Train nowadays using 3 phases. You have pre-training phase, where you take a bunch of data and just order your recipe, predict next tokens. And then you have this instruction tuning phase. So you're giving it human demonstrations of example inputs and completions that you want the model to perform through human instructions and fine-tuning on that. And nowadays we also have this post-training test time scaling phase where you can ask the model to think and search over multiple possible trajectories to get the right answers. And you see some capabilities, QA, both retrieving knowledge from the internet and also retrieving knowledge and answers from its own weights, open-ended dialogue, translating different languages, retrieving news and real-time information. And nowadays, problems on the reasoning side, so solving math problems, writing code, doing things that require you to break complicated problems down into step-by-step, solve those local solutions, and then wrap things up and explain it to people in a reasonably interpretable way, and more. And so David talked us through all this recent progress in large language models. And now, of course, we want to go from large language models to large multimodal models. LLMs as themselves, they're still just only taking in text. They're not grounded to real-world sensory information. So the biggest difference, one of them is on the input side. So ideally, they might want to take in videos, and these videos that I've shown.
It's just a privilege to watch your mind at work.
So videos of people, social understanding, social interactions, sensor data, real-world physical data, robotics data, getting these LLMs that actually be grounded and understand the real world in all of its different mediums. So what are some challenges and what is the progress in these large multimodal models? Here is, a way of the timeline I currently see and where we currently at. So we started with multimodal models that understand the world and do simple things like classification. So classify into a set of things, the tone and behaviors and objects and other discrete phenomena. And nowadays, of course, you can still ask these models to answer classification questions. You would just ask it as a question and maybe give it a list of possible answers. And from classification, we became more open-ended. So in addition to asking, is it happy, sad, sarcastic, not sarcastic, you can ask, describe the relationship. So going beyond one-word answers to open-ended dialogue grounded in this case, videos. And then we have works that further extend this to explaining. So not just giving answers, but explaining them. So You might want to ask the model to explain why. Why are these two people sarcastic to each other and seem to hate each other, even though they're clearly long-term friends? So the model might explain why in language, it might cite visual evidence and facial expressions, and it might even retrieve previous episodes to supplement and justify their decisions. So we are currently at this explanation phase. We have gone from classification, open-ended back and forth dialogue, to reasonably good explanations with some step-by-step reasoning grounded in multimodal data. And then you have things that are, of course, even harder, right? Can you use this short video clip as a prompt to further generate animated story? This is the starting prompt. So that could be the instruction, and the model might generate video, audio, language, animate those characters. And finally, even counterfactuals. What if you ask a question like, what if these people were from a different society or culture? Or would this sarcasm still be seen as humorous, or offensive? Who might it offend? And can you justify that? Can you even generate more data, video and audio to justify that? So going to more difficult cases, and right now we're kind of at explanation, lots of interesting progress in multimodal reasoning for explanations, and nowadays also multimodal inputs, multimodal output, so that you can get towards generation and counterfactuals. So this is the general schematic of how I see a lot of these models will go into the future. It would take in language, it would take in other modalities, it would learn language and multimodal representations. And from this, it would be able to continue generating text. So the language models are grounded, and it could generate other modalities, and it could do this over multiple steps of dialogue and interaction with people. Right? So this is general schematic of how these large multimodal models will progress. And so today in the lecture, we'll cover each of these parts. In the first part, we'll just review, so we've seen some of this work before, and also cover some latest work in taking in different modalities, often temporal in nature, and learning these representations using foundation models to get these really rich representations. That's be part one. Part two, we'll cover how we can take these multimodal representations we've learned and quickly adapt them so that they don't just be used for classification, but it can be used for language model interaction and dialogue. And finally, we'll look at part three on how we can go beyond generating text to generating other modalities in the input and output. So we've seen, part one for learning multimodal representations, we've seen transformers for language. You'll recall we can also apply these transformers for vision. And essentially nowadays, anything can be roughly tokenized into some discrete parts and thought of as a sequence. So language would be a token of words, image would be a sequence of image patches, video can be a sequence of frames, sensory information can also be seen as a sequence. And these transformers essentially learn your self-attention over those elements in the sequence to learn increasingly informative representations. And of course, multimodal transformers are a backbone for many of these models today. The biggest difference between multimodal transformers and single modality transformers, as we've seen earlier in the class, is that now you have your query and keys coming from different modalities. So query could be from language, in this case, 3 words that a person is speaking with some dimension. Your key embeddings would be from, in this case, nonverbal. So there might be some vocal features, there might be some visual features over 4 time steps. And in this case, it's transposed, so it's D by 4. And in this case, the D has to be common. The dimension has to be common. So the dimension of your projected language embeddings and the dimension of your projected nonverbal embeddings. They have to be similar because you want to think of them as this underlying common multimodal space in which you are measuring alignments and similarity scores. And that can only be possible if you have the same embedding space. So this WQ is the transformation that takes in your language and goes into that space. And your WK is the embedding for your nonverbal and brings them into that space. And you can recap, this allows you to get your 3 by 4. This is your cross-attention matrix. Instead of just words and other words, it's now words with nonverbal expressions. So it's 3 by 4. And the standard normalization stuff that we've seen in transformers, normalizing by dimension and normalizing by your softmax. So you want to view this as a cross-attention between your words and your nonverbal expressions. So privilege might have some alignment of 0.7 to your loud voice, because he's saying privilege in a loud voice. And privilege might also have some attention with your eye rolling. performing an eye roll after he said the word privilege. So this can be seen as temporal attention because it doesn't just have to be attending to the same thing, same expression at the same point in time, but it can be also very later in time or earlier in time. Of course, this alignment is not the only thing that we hope to learn. The goal is to use this alignment to learn better representations, right? So you can then take the multiplication with the actual nonverbal features itself to get a new representation of language. So now this word privilege has taken attention of 0.7 times the vocal emphasis embedding plus 0.3 times the eye rolling embedding. So it's contextualizing itself by looking at all the 4 nonverbal features, figuring out what alignment weights to assign to it, and actually taking the weighted average using those weights. And now this new multimodal representation can be used for doing any inference, such as in this case, predicting sarcasm. So these multimodal transformers, extension of language-only transformers, are used in virtually all of these foundation models today. They started with just training transformers from scratch on data, and then you started pre-training these transformers. So it was very common to have sequences of images and sequences of words. You would apply these new transformers within each modality, and you apply these co-attention transformers. So the language can attend to vision, and the vision can attend to language. And oftentimes you do it in both directions. And then after you do that, you might have more transformer layers to eventually get features. Now, after multiple layers, language has attended to vision, vision has attended to language. You get 2 sets of asymmetric multimodal representations. So they may not attend to each other in the same direction. And that can be useful sometimes. Vision might require more dense attentions because there's many parts of the image, and language might have more sparse attentions because there's fewer words. So it's important that you do it in both directions and you get something that may be asymmetric. So then people started pre-training these large transformers, so you could get a lot of data. In this case, unlabeled data, so a bunch of images and a bunch of captions. You could just download this as scale. You can apply these transformers that does this cross-attention, with language to vision, vision and language. And then people explored all these different prediction tasks. So all roughly self-supervised in nature. Unsupervised in nature because you didn't need humans to label them. So you could do mask language modeling. So you would mask out certain words, and you would try to use the surrounding words and also the image regions to predict those words. So the more words that you mask out, the more you're forcing a model to translate from visual to predict the words. Then you would mask region modeling, so you mask out certain parts of the image, and masking out the image, and you use the remaining parts of the image and the caption to predict what was masked out. So that's masked region modeling. And all this is done at a more fine-grained level, as you can see, and here is a more global level. So you would take the entire image with all its patches and the entire text with a whole sequence of words and try to match those. So this is your classic contrastive learning objective. So this whole image is this caption, and this image is different from this other caption. This is sentence match the image. So people explore with a lot of different objectives, some vision to language, very fine-grained at the level of words, some language to vision, very fine-grained at the level of small image regions, and then some more global, where you have all holistic image with holistic caption. Okay, and these were examples where we show that some of these attentions and alignment scores seem reasonably interpretable. So you could, all these small boxes are the resolution of patches that you're cutting the image up into. And you look at the attention going out from the word flowers, this cross-attention matrix, it does highlight the region with flowers. And you look at the attention from wall, it does highlight and keep the image patches with a wall as having high attention weights. Cottages at the top, cloudy in the background. And here's just more examples. Right? So nothing extraordinarily new. We've seen examples of language transformers, vision transformers, multimodal transformers, and different ways of pre-training them. This partially as a recap. Okay, so that's this part. Also sequential data, temporal in nature, learning these representations using cross-attention models. And now, of course, you want to adapt these representations as input into language models. So this allows you to have the flexibility to ask and answer any questions that you want about your multimodal context. So how do we do that? Another key idea that has emerged is the idea of adapting LLMs. So most of the times, these LLMs that you've done and trained are huge. So ideally, you want to keep them frozen. You don't want to update them too much. You don't have the computational resources to update them. And one good, interesting idea is that you can essentially take in any data from any other modality and define what we call adapters. So in this case, you have an image. You pass this image through image features, and these can be pre-trained CNNs or pre-trained ResNets, vision transformers, and you get these feature embeddings from these images. And then you would define an adapter, and you want to think of it as a very small transformation that takes as input these image features and outputs something that is of the same dimension as your language model token embeddings. Essentially adapting image features into the input of these frozen language model token embeddings. So once you've done that, you can put it as the prefix. So before you actually start seeing the words and the token embeddings of these words, so you put it as the prefix and essentially concatenate all those together. So image features adapted, followed by the rest of your words, and put that as part of a pre-trained model. So now this pre-trained model would try to understand as context at the start, image features that have been adapted into token space, and also the token embeddings of the actual words themselves. And how would you train this model? Well, first, the only thing to train here is the adapter. So ideally, this adapter is really small. People have shown that it can even be a small, just linear transformation is sufficient. That's the only thing that's trained. This vision model, language model is usually frozen. The vision model you can train or you can fine tune or you can keep it frozen as well. And how you would train it is that you would take a bunch of images, a bunch of captions, and you would try to predict autoregressively the next words in the sequence using as context the image, adaptive features, and the previous words that you've already predicted. So you would need some amount of paired data between image and text to train these adapters. So once you train it, you can do many cool things. You can give it a new image, ask what color is it, it will give you the right answer, even though it's never really seen examples of images and questions before. It's only ever seen just text and maybe text questions. If zero shot isn't good enough for performance, you can give it one shot. So you give it one image, you give it a question, who invented this, and give it the answer, the Wright brothers, and then you autoregressively predict these words, and you give it a new image here, and you ask, again, the same question in the same format, who invented this, the model gave the answer, Steve Jobs. Right? So this is a kind of one-shot question answering. And again, the only thing that's being trained here are these adapters. The language models are frozen. And finally, you can do several other cool things. This is what people call a symbol binding problem in psychology. So how well can you remember names of different parts, objects? So here you give it an apple and you give it a caption. This is a DAX. So DAX is meant to be a made-up word. And you give it another image of an orange. You say this is a blicket. Blicket is again meant to be a made-up word. And then you give it a new apple-looking like shape, different orientation and color, and you ask what it is. So using these 1-2 examples, you can generalize and say, this is a DAX. So you can bind these new names to your objects fairly quickly. So this, this paper kind of kickstarted this, few-shot learning, multimodal few-shot learning, using these, frozen LLMs. Whereas previously, people were still training image and text transformers together, and it was still mostly supervised learning. Now you could just take frozen LLMs with very little image data, very small adapter, already start seeing these evidences of multimodal capabilities, like image question answering and image captioning. So that was 2021 by Google DeepMind, and then they further scaled this up to get the Flamingo model in 2022. So yes, use this model. And again, this directly uses these adapter-based methods from frozen LLM and adapting image information. And whereas previously I mostly showed you just examples of short completions, when you scale it up, you can see evidences of much longer-term dialogue-based completions. We give it an image, goes through the image embedding, goes to adapter into language model, and you can start having conversation with it. talking about two teddy bears on the moon, talking about flamingos in different styles. And some of you might have seen this on social media, earlier versions of these vision models. You take this photo of Apple, you paste the sticker iPod on top of it, and vision models will classify it as an iPod. And this flamingo model is able to recognize that it's actually an apple with a sticker on it, and the sticker says iPod. Although I wouldn't take too much stock in some of these viral bugs being fixed, because these tech companies, people are probably on Twitter looking at all the funny failure cases and adding that as training data into the model. That's Flamingo. Nowadays, GPT-4, no one really knows how it operates, but some people have tried to do smaller open source versions of it. They found that, again, these adapter layers are pretty general. So take an image, put it through a frozen model, so Q-former, vision transformer, training large amounts of images, frozen Vicuna model, open source instruction following language model. And the only thing that you're training here is this linear adapter layer, linear transformation from whatever this dimension is to whatever the token embedding of language model input dimension is. And nowadays, these models are usually trained in several stages. One stage is alignment. So you first take in a bunch of images and their desired descriptions. So you can get some image captioning data sets, Wikipedia, Instagram, or the like. And you basically train this linear layer to take in the image and describe the image exactly. So that's called alignment with paired image text data. But of course, we don't always use these large vision language models only to caption images. We also try to use it to solve interesting problems. Right? So one example is, given this kind of like graphic design flamingo image, you might want to ask the model, what do you think about this? Imagine you're a graphic designer assistant. So the second step is to do instruction tuning. In this case, visual instruction tuning. So you give it some images, you will give it some, so you ask humans to annotate some instructions that they would like to see completed for those images, and you have the same people write the good answers, good desirable answers. So you do instruction tuning using image, text instructions, and example completions from people. And but same thing, when you do instruction tuning, this image comes in, goes through the linear layer, the instruction that humans have annotated goes in, and then you do supervised prediction of each word in the desired answer. And only a linear layer is being trained. And afterwards, you would basically just deploy this and do all your standard post-training human feedback stuff. But back then in this 2023 work, they didn't do all the stage 3 post-training. So this is technically stage 2. Yeah. So this is example for stage 2, because now you're giving it an instruction that is beyond just caption and describing the image. So stage 1 will be, you take a bunch of images and their captions and just describe, only about descriptive describing of the image. And stage two is more open-ended. This, what do you think about this logo, is more open-ended. Got humans to basically annotate some tasks they find interesting and good answers, completions to those tasks. People have really scaled these adapter models up to really lots of modalities. So Llama Adapter is a good open source community that has been built around this, based on Llama, the Meta's LLM, which is open source. And it basically consists of a bunch of adapters, right, for different modalities. So image and image representations and the pre-trained adapters into Llama input space. Here's an example of 3D point clouds that a model that this thing also supports. So 3D point clouds goes through some 3D point cloud representation model, and then you pre-train an encoder into the Llama input space. Now you can do things like give a 3D point cloud and give an instruction like generate image corresponding to this 3D point cloud. So all that would go into your pre-trained, frozen, and adaptive LLM. And in this case, they also stapled the text-to-image diffusion model as the output, so you can actually generate some cool images. Okay. Also, they support multiple languages, so different adapters for different languages. So this is a good open source resource. And finally, speaking about the data side, of course, this, again, couple of stages, pre-training, just for you to know, most of you might not be downloading or pre-training these data sets, but size has exponentially increased in size from YFTC, which was more image and caption pre-training, to Lion, 400 million, became Lion 5B, and Datacomp is this most recent addition of open source image text pre-training data of 12 billion parameters. That's 12 billion data points in size. Another transition is that previously people just took one image and one caption. A lot of these were just one image and one caption, and that's how you pre-train models. Increasingly nowadays, people are looking at interleaved image and text. That means you have image, caption, image, caption, image, caption in a sequence that more naturally follows how you would, for example, draw and text your friends. So not just one image, one caption, and the next one is independent, but rather a longer sequence of interleaved image and text. And as I'll show you later, that's enables some cool new capabilities. And also recent efforts have also kind of shifted to interleave, but also higher quality. People have realized that some of these things are really large and lots are not good and not useful. Some also have very explicit graphic images inside of them. So nowadays there's also another trend of filtering smaller and high quality. So there's Obelix and DCLM are some popular resources. So they're smaller, but they have higher quality and also interleave image and text. So that's pre-training. Instruction tuning, more scattered, smaller in nature. This table gives a survey of different instruction tuning data sets. So again, in this stage, you don't just have images and captions describing each other. You actually have images and people describing what they want to do, and the right answers humans gave. So these are all examples. Mini-GPT-4, as I covered, it was probably one of the earliest examples. Only 5K instances. Didn't really have any tasks. People just randomly did stuff, and it wasn't multilingual. And then Lava is another popular instruction tuning, visual instruction tuning database. Instruct Blip, so a pretty popular one. And those have gone up in size, but their order is basically in the couple millions rather than the billions in the pre-training regime. So these are some for general domain, and of course, there's a lot of instruction tuning that are specialized for domains. So David did recently his climb that he showed 2 weeks ago, which was large-scale instruction tuning for medical images and medical questions that doctors might care about. And then LavaMed, Biomed, these are all other medical examples. So a bit more focused instruction tunings. All right. So in this third part, we've seen now in the first part, multimodal data, usually sequential and temporal, learning multimodal representations using transformers, and how you can quickly adapt that into a large language model. And of course, the next part, as we alluded to in the Llama adapter part, is to also be able to generate more multimodal data as you generate text. So generating images from descriptions, images from point clouds. If you want to highlight relevant episodes or retrieve evidence, it's also a visual and audio generation problem. So we're going, recent trends are going from text generation only to multimodal generation. Of course, some of you have seen these examples of text to image models, lots of really cool, fancy DALL-E stable diffusion-like models. We'll cover this in more detail in about 2 weeks. But right now, I'm just going to assume that we've seen some of this, and we'll look at how we can integrate them into these multimodal LLMs. So lots of fancy examples. Quick recap of, just quick introduction to how they work before we go into detail in the generative models lecture. First, lots of images, and you can just use image only to train really good image encoders and decoders. Right? Some of the best state-of-the-art image encoders nowadays are based on CLIP. Probably seen that. We talked about it in class, where you take lots of images and captions, and you train this contrastive representation learning so that the image representations that you get from CLIP are not just independently separated from language, but are already very close to language representations. So that's CLIP is nowadays used as an encoder. There's a model that translates text that comes in through a transformer, learns representations, and is transformed and translated to predict the CLIP image embeddings. And this is where, using a clip really helps, because if you're using any other pre-trained vision model, then this distance will be very far away from each other. But now that you're using clip, this is really quite close to language space based on how clip was trained using contrastive learning. So this mapping can be done much more easily. So clip to encode the image, language model to encode the text, and to map it into your clip image embeddings. And finally, from image embeddings to the raw image itself, diffusion models, right? Diffusion models that generate pixel by pixel. And nowadays, increasingly, flow matching models are coming as a competitor and sometimes even outperforms diffusion models. And we'll cover the generative models more in 2 weeks. So how do we use these text-to-image models as part of this whole multimodal LLM pipeline? So here are some papers that are quite recent. So again, one innovation is this idea of interleaved images and captions. You want to train your model using given an image. As you see, the image goes into a visual encoder, and you have these adapter layers that we've seen. And then after this image, you have a caption for it, so silhouette of a plane against the sunset. And then you might have more images that go through the visual encoder and the adapter, and you have more captions, like cat sitting on top of a scooter. So you have a sequence of image and text that are all either adapted to the visual encoder or tokenized if it's already in text. So that becomes your whole input embedding, which goes to an LLM. An LLM could generate next tokens to complete the story. And it could also generate embeddings that you could compute a similarity with respect to image embeddings. So by computing this similarity, you can basically retrieve which images might make the most sense as a completion in the output space. So silhouette of this plane, which is the story that the model had just completed, that would learn some language embedding. Info in CE is your contrastive loss to find the nearest visual embeddings, and you would search over your images to find the one with the closest visual embedding.
What's the benefit of interleaving?
You see in some of these examples, when you deploy this model, you'll want to interact with it multiple times using language vision and generate language and vision, and you want to have this continuity, right? So if you only give it one language and image and ask you to generate one thing, then you're not going to be able to have this continuity when you eventually interact with it. So here are some examples. You can start talking, thinking about some animal, try to guess what it is, and then show me an illustration. Either show me a pencil drawing of it, you can tree something, show me another photo of it. Here, start with some house with some architecture design, talk to it, and then show me more houses. You can retrieve similar houses and even more. And over here, it's an example of cooking. So you do back and forth dialogue. At some point, you want to see what it looks like. You can retrieve the nearest cooking image, and you can even continue that. So all of this, several key ideas: interleave image and text, using training, learning image and text inputs, and then on the output is generating more text, and also generating an embedding, which you can compare to clip embeddings for images to retrieve the nearest image.
Is it like you did that for the model, not just language, but also multiple images?
Yes, although it is not really keeping image embeddings in memory, as you see in this case, it is taking images and it's going through the adapter to language tokens, right? So it's kind of projecting everything into language space. And language is a memory that a model is using. And when it's trying to generate images, it's outputting the language embedding and it's using clip to find the nearest image. So it's not keeping both. It's the bottleneck. There's a language bottleneck, basically.
Is there any difference? The term is the same, so I'm not sure if it's related or it's
What context do they use it in?
I'm also not super sure. It's like in a few papers that I've seen this idea of using a codebook to generate
Yes, the word codebook is used a lot nowadays. I think people just love using it to mean anything discrete, or like a dictionary codebook. So when these image encoding, decoding models first came out, people love using vector quantized VAEs. So you took continuous images, project them into discrete embedding space, and call it a visual codebook or visual dictionary, so a discrete bottleneck. I'm sure maybe some people have used that term to describe stuff here because everything is still, you're projecting stuff in discrete tokens, whether language tokens or visual adapted tokens, and the retrieval is also over a discrete codebook of images. So maybe that's what they're referring to. But people love to use that word, and people love to have just discrete bottlenecks and stuff nowadays. So yeah, speaking of discrete, this was retrieval, so it only works over a set of discrete images. The good thing is that you're guaranteed to generate a realistic image, or you're guaranteed to retrieve a realistic image. The downside is that you're limited to what images you're retrieving over, and sometimes it can be slow. So naturally, the extension was to go from image retrieval to image generation, right? Pixel by pixel generation. But the idea is also very similar, same authors. Image goes to visual adapter, language is captioned, there's some interleaving that's going on. And once that sequence is going to LLM to generate the outputs, there's some decision model to decide whether to retrieve. And in retrieving, you're just using the Eclipse similarity to retrieve images, or generating, in which case SD is using stable diffusion to generate text to image pixel by pixel. And sometimes, they found that sometimes retrieval works better, sometimes generation works better. So the example here was a couple of cookies that you might have just baked, and how you could best display them at the farmer's market. So the retrieval model is something like this, which is kind of stacked up, tied together. Generative model gives you generate something which is more spaced out. Or of course, you realize that these are not the exact cookies, right? They actually look very different cookies, but they have a very different layout. And maybe the final model would then aggregate these and say, I think they look better when they're on a tray spaced out. They give you back this generated image. And more examples. So one of the popular data sets that people use nowadays is this data set called visual storytelling. So it's also a big interleaved data set where you can have stories of text and images, and more text and more images, which has been used to train and also evaluate these models. All right. So now some latest advances. We've talked about adapters a lot. It's been a trend to have frozen LMs and an adapter that just quickly adapts this LM to look at multimodal context. But I'm sure some of you have seen Llama 4 in the last week. And Llama 4 claims to be this native multimodal model, and they made a big deal out of that. So there's been a kind of a battle between whether pre-training language, freezing it, and adapting multimodal information is better, or whether native multimodal models. So essentially, these models don't start with a pre-trained LM, and they try to train language and images and video and more modalities together from scratch, right? Of course, it's something that only big companies can investigate nowadays at their scale. But Llama 4 really made a big deal of how their method was natively multimodal, this native multimodal with 1 million context length. I think the biggest advantages are if you can afford to, then there's a lot more information to be discovered from images and videos, and we're really exhausting how much text we're training these models on. That means you don't start with a pre-trained LLM. You start with nothing, basically. You start, yeah. Yes, so you give the model language data, video data, audio data, and whatever more, and you're basically training from randomly initialized parameters, language representations and language vision representations and video representations. So you're not training the model for like a couple of months, then getting already good language model, and then only adding multimodal information. Biology and people psychology background, they also love this because they feel how humans learn and how children learn is that they learn about visual and audio and moving around, sensory motor, before learning language. And that's how evolution taught people how to learn. But then, this came out, and then this was very disappointing. It didn't seem to be as good. And then, again, we don't know how 4.0 and Gemini are being trained. I think, it's probably a mix of pre-training and adapting, and also like some native components. Okay, but it is also the largest model now. I think the largest ones to be 2 trillion parameters. And here's basically a difference, right? For non-native VLMs, image encoders are paired with frozen trained LLM. And the image encoder, there's some flexibility, it can either be trained or fine-tuned or frozen. And nowadays, most VLMs use a structure, especially the ones that you would use in your, that you see in the papers, that people play around with, that people try to extend to more modalities. It's usually the structure. And it's really plug and play, more modular plug and play. You can change this to a sensor model and a sensor encoder. And with some amount of sensor language data, you could train a sensor LLM. So it's non-native. And then for native models, they train from scratch multimodal inputs. There's methods that do late fusion. So it goes to image encoder, and then it already has good image features, and then the training text together jointly with it. And there's also methods that do early fusion. So they don't even have pre-trained image encoders. They're kind of just taking in pixels and trying to embed pixels or image patches into LLM. So at what level the image model goes to LLM also is some engineering question. So with Meta's release of their Llama 4, they also released some scaling laws for these natively multimodal models. This one, if you recall, we had a reading on scaling laws for this mixed modal generative models, right? That was also by Meta, so I'm sure there was some inspiration there. And so like that scaling law paper that everyone read for that a couple of weeks ago was also a natively trained multimodal model. Right? They had text, they had some speech, and they were either training text from scratch or speech from scratch or text and speech together from scratch. And this is just, nowadays their newest version of their scaling laws. Some key takeaways seems that early fusion models hold small advantage on small scales, and on larger scales, both architectures perform quite similarly, both early fusion, so you're directly operating on image patches and transformer, and late fusion, where you go through pre-trained image encoders. So maybe we might not need image encoders. And these natively multimodal models also scale similarly to unimodal LLMs with some different constant factors in their scaling exponents, which may be a good thing, which means that saying all the work in scaling LLMs could also be translated with some constant factors to scaling these natively multimodal models. Of course, scaling these like pre-trained and adapted multimodal models and those scaling laws, I don't think people are really studying. And maybe it might not make much sense to study because it's probably going to be bottlenecked by just the scaling law for the language, pre-trained language part. This is a cool paper. Yeah, so several other recent advances. Llama 4 also had mixture of experts. GPT-4o and Gemini, I don't think they mention mixture of experts, but I think Llama 4 is the first to openly mention mixture of experts for these multimodal models. They say it significantly benefits these natively multimodal models at the same inference cost. And also in the MOE structure, modality-aware design. So if you have separate image and text experts, that's actually worse than modality-agnostic design. So ideally, you want to have these experts that are agnostic to your modalities. You don't want to partition your experts too much based on which modality. And that was some finding they had. Okay, this paper is pretty good. We've also been doing some work on these multimodal mixture of experts ourselves, of course, not as big of a scale as Meta. So one thing we found is that you could take all these videos, and if you recall this RUS, we looked at these different ways in which modalities interact, right? Sometimes the information is common and redundant in both. Sometimes there's a lot of synergy, and there's different degrees of synergy. So you take Blip2, one of these pre-trained video events, you see that they work really well in exploiting cases where information is similar, but they really struggle with lots of new synergy and new information that emerges. So one type of expert we've been designing is that you could take your data and you could essentially classify where the information comes from. And based on where the information comes from, you could design separate experts. One expert to look at both and capture the commonalities, one expert to do fusion and capture synergy, and maybe more experts to do synergy because that's harder, and some experts to do uniqueness. And there's also a general mixture of experts layer that can be applied on vision language models or that are native or LLMs that have been adapted or just LLMs themselves. So yeah, so we saw some boost in performance, especially for the types of data points that the model struggled with the most at the beginning. So this multimodal mixture of experts. I thought I should also mention lots of interesting work going on in time series LLMs, mostly in the pre-trained LLM, keep it frozen, have some time series coming in, and then running some sensor encoding model and adapt it into the frozen LLM. So time LLM, one fits all examples of this. And what are the tasks? There's classification tasks on sensor. You can also literally ask the next value is and have it output something like 0.6, like tokenized numbers, which is pretty interesting. But doesn't work really well yet. So people found that most of these current time series LLMs have questionable performance. Sometimes you can remove some of these complicated attention layers or even the frozen LLM, replace it with a simple attention layer, you can still see pretty good performance. So unclear where the result of this with LLM and without LLM, the performance doesn't really change that much, like 0.003. So lots of interesting stuff. Yeah.
How do you inputting the time series?
Yeah, I've seen a couple. So some of these time LLMs, they have designed a custom time series representation models. So they train transformers for time series. And that's another active area of research. I've seen people like plot it out, save it as an image, put it as an image. That seems actually intuitively that works quite well. Surprisingly, works quite well. And then there are people who put numbers, they literally input numbers, and you would think that doesn't work, but I've seen some people claim that it works. Like some people who do robotics nowadays, they literally put as text, the angle of this joint is like this 45 degrees, and the angle of this joint is like this, and the proprioception is like this. I literally put it as text and numerals. The model seems to be able to do something with it. So a couple options.
Yeah, because I think I also was looking into time series, understanding that maybe solve people using my structure going, it's more interesting in the treatment, but I haven't seen one that will actually compare between this structure actually.
Yeah.
Rockets. I was wondering if there's like
I mean, we start with this. This is a very comprehensive study, critical study. I'm sure they tried a bunch of models. I don't know if they study different encoding representations, but they probably have all the data and models set up, so you could try that if they didn't. All right, so to summarize, we saw recap and multimodal foundation models, transformer architectures, and how they're generally pre-trained, some evolution of methods over the years. Nowadays, a popular approach is to adapt frozen LLMs into their multimodal counterparts by training these modular adapter layers. Also a big trend on going just from text generation to having multimodal input, multimodal output. So enabling true multimodal interaction. And some latest directions in natively multimodal mixture of experts and extending to actual real world modalities. Okay, that's all folks. Just a quick recap of the assignments. I'll be around, and David and Chanakya are also around, so please meet with us. We should try to get either promising results and a path to scaling or not good results, but a good idea of how to fix. And remember to submit a reading assignment tomorrow for this Thursday's discussion. Thanks, everyone. Yeah. Maybe easier to just discuss it.
we should respond to finding.